but it will take me a while to get there. So I want to start by doing a lot of algebra, and in the end, the algebra will serve some geometric questions, which is my goal in this discussion. Now, I don't know how much ordinary algebra everybody knows, homological algebra everybody knows, so I started vaguely from the beginning with this. You can tell me that you know all this and you're uninterested. So I start out with a commutative ring with unit. And if I have P as a projective module, over R, if given an epimorphism M onto N and a mapping, a homomorphism from P to N, then there is an extension V bar from P to M, making this diagram commute. So I assume everybody knows about projective modules, right? Or no? Yes? No? Is it okay? Is this the right place to start? Or should I jump way ahead? I don't know. So a projective resolution of a module is an exact sequence of this type with pi projective for all I. Okay, so that's a well-defined notion. I guess I'll denote these by these mappings between the p's by a differential d, although obviously since this is exact, we're not interested in the homology of this sequence. But I will point out that M is the homology of the sequence that stops at 0. So in fact, it's of course interesting to think about replacing all modules over a ring with projective resolutions and just simply stopping the projective resolution here, because you then get all modules out that way if there are enough projectives. So I believe that this is the basis for the derived category, although I don't play in that arena very much, but that's my impression. So if M is a right R module and N a left R module, then of course we can form the tensor product. Just simply take the Vn cross N mod the identification like this. And so the first thing that I'm interested in is what happens when I think of this as this construction as a functor. So if I take the functor that associates to m tensor r over n, and f from m to m prime goes to f tensor 1 from m tensor n to m prime tensor r with n. So I'm interested in studying this functor, and if the following is true, if I have a short exact sequence of right R modules, then K R with N, Q, M tensor, then Q, R with N 0 is exact. So in particular, you don't get this 0 here, and you get a sequence. So what happens here? And in order to fill this in, you get a sequence of derived functors. So here's what happens here. You get tour 1 of Qn tour R1 of Mn R1 of Kn tour 2R of Qn, etc. So in order to complete the sequence into a long exact sequence, we pick up a set of modules that fill this picture in, and they behave like a homology theory, like a cohomology theory, and fill in this. So in particular, the groups tour NR MN are defined by doing the following. You take the sequence that you obtain from the exact sequence of the projective resolution. You take the projective part of the projective resolution, you tensor with n, and then you take the homology of that. The homology at the nth stage of this will be the definition of the Tour group. So my point in reviewing all of this is to say what Tour is doing. So the Tour measures the deviation from being free on tensoring with n. So that is how I'm sorry, yeah, on being exact, being exact on tensoring with n. That is, if I take the functor here, m goes to m tensor, and how much does that fail to be an exact functor. It also measures the deviation that M has from being free, because, from being projective, because it's built upon the projective resolution. And so when M is projective, of course, there is a very nice short resolution with just M that is there, and hence the higher Tor groups in the higher homology would all vanish because the module was already projective. So Tor is measuring the deviation from being exact and the deviation from M being projective. It's, of course, somehow symmetric in M and N in the sense that N, of course, is, I'm talking about left modules here, and I could have resolved N by projective left modules and tensored on the, and then done everything for tensoring on the left by M. Or in fact, I could have resolved both modules and taken some kind of a total complex in order to obtain the homology. And in all those cases, you get the same answer. So, this is an algebraic setup and an algebraic framework in which to discuss some topological issues. So this is the situation that we're in. First of all, I mentioned in the first lecture the Leray-Sayre spectral sequence. And the Leray-Sayre spectral sequence begins with a fibration from which we take data of, say, the homology of E of B and the homology of F, and take that data to put together the homology of E. So in this case, we're going from the base and the fiber to the total space. So a question that one can ask that's a reasonable question is it possible to do other combinations? So for example, can we go from H star of E, I think I'll change the cohomology here, H star of E and H star of B, and compute H star of F. The examples that I have for this are somewhat important and interesting. So, for example, we have the path loop fibration. Loops on X in the paths on X over X. And the important feature of this, of course, is that the path space is contractible. And so, in fact, it's quite easy to know that we have information about the total space, and potentially we know information about X itself. Is it possible then to go from these bits of information and go back and obtain the cohomology of the loops on X? So that's one example of this question. Another example is the case where I have a situation like this, where this is, say, compact Lie group. And this is a closed subgroup. Under these circumstances, I have a long exact sequence of homotopy groups. And what I'd like to do is think about these actually in the following way. And I realize that I'm potentially introducing something that the students haven't seen yet, but this will be the Q plus first homotopy group of the classifying space of the subgroup H. So I'll just assume for no good reason that everybody knows what classifying spaces are. If you taught, is that how you teach characteristic classes? Teaching using, do you teach characteristic classes using classifying spaces?
No, I haven't specifically mentioned that.
Well, no, yeah, no, that's a bad thing. Oh well. We'll talk about it. I'll try to fill it in. But everybody should go out and learn about classifying spaces. Very important. Right.
Many of them know, but
So many of them know. Okay, very good. Yeah. So let me write this as in this way. And this is this and this. So under these circumstances, if I write it this way, then this suggests a fibration of the following sort, where the fiber is G mod H, and the total space is the classifying space on H. And the base space is the classifying space on G. I'll put in one simple property of the, so it's an aside, and that is that there is a fibration for the classifying space, which has the following shape. It's G inside EG over BG. And EG here is a contractible G space. And so this, in some sense, characterizes the classifying space of G up to homotopy. So in particular, you get the loops on BG, so on top of G, and so you can if you, that should be sufficient for good topologists to know enough about BG to know what a BG is. Okay, so that'll be sufficient. So this suggests that there's a fibration like this, which means that if I'm a couple of things that are of interest here. First of all, if I could compute the cohomologies of these things BG, then using these cohomologies and being able to go from the total space and the base space back to the fiber, I would be able to calculate cohomology of these homogeneous spaces by this method. And so calculations of the cohomology of Lie groups, you would need a step which went from the cohomology of the Lie group to the BG, and then from that be able to calculate these cohomologies and then work back to that. So all of that are a couple examples in which computing the cohomology of the fiber from the cohomologies of the total space and base space are important examples. So let's see if we can figure out how to calculate this. And I want to place this in a somewhat more general context. So let's introduce the general context. The general context is the following. I'm going to start out with a fibration. With fiber F, and then I'm going to take a mapping some function x, and what I want to do is form the pullback over F of the fibration P. This gives a new fibration E naught over x. And so the problem, well, let me first show that if I take some fibration and I simply map in the base point here, then the pullback, E naught, is pullback. It's the set of all things of the form xe such that f of x equals p of e. And this can be topologized as a subspace of x cross e. And of course it has the just simple projection down from either factor gives the maps that complete that diagram. So that's the standard construction of the pullback. If I look at the pullback in this case, then I just get the fiber, because I'm going to the base point, so f of the point is the base point, and so I'm looking at the inverse image of the base point, which is the fiber. So, so this question here, can we go from this data here, is an instance of a pullback diagram, and the general question that we want to ask here is, can we compute cohomology of E naught from the information that we have, which is f from x to v and p from e to b. So that's the situation we're in and the question we want to answer. So here's how to think about this, and so let's write down first the pullback diagram. This gives rise, so let's just apply the cochain functor, and we get cochains. Let me suppress the field here. And I guess P star and F star are part of this. So, the thing to note here is that we have extra structure from the cup product. So in particular, this implies that I can write C star E as a left C star B module, where the action is given by simply doing P star tensor 1 to C star E, tensor C star E, and then the cup product brings me to C star E. So this I get automatically from the existence of this this ring homomorphism up here. And then likewise I get that C star X is a right C star B module, where I simply induce that by the same way. I should point out that the cup product at this stage is not a commutative thing. This is just some algebra structure that's on these vector spaces, and so you know it's not so simple to assume that things commute, and so one should make one's calculations with that in mind. Well, okay, so here's the first guess, which is that C star E naught should be somehow C star X tensored over C star B and C star B. Okay, this would be great. This would be great because somehow that would mean that sort of pullback diagrams correspond to tensor products over these algebras, and it would be a nice thing. So, let's notice if B is just a point, this works. B is just a point, this works because then here essentially I'm looking at the pullback will be X cross E, and that will be isomorphic to C star X tensor C star E. This is the Eilenberg-Zilber theorem, and so the Eilenberg-Zilber theorem is a situation in which your first guess turns out to be correct. However, it fails for the first vibration of any interest. Let's see, take the Hopf vibration and do this calculation and try to compute C star of S1 from and this fails fairly miserably. So So this is obviously not the way to go. But let me ask, of course, what is it that makes it work in the Eilenberg-Zilber case? And well, the reason it works in the Eilenberg-Zilber case is that if I'm looking at the chains on a point, which I replace with just the ground field, everything is projective over the ground field. And so one can say, well, the reason that this works is that that this tensor product that I'm forming over the ground field sees everything as projective. And if everything's projective, of course, it works nicely. So the failure to be projective is what's in the way of such a guess working. So as I introduced in the beginning of the talk, we have a way of measuring the failure to be projective and the failure to be, and that's via the Tor functor. And so let's add in the measures of failure to be projective. And we get the following theorem of Eilenberg and Moore. That is that H star E naught, I should put this as, these are actually two theorems. The cohomology of the total space of the pullback is isomorphic to Tor over C star of B C star X C star E. And two, there is a spectral sequence with E2 isomorphic to Tor over H star B. H star XK H star EK converging to Tor C star B C star. So in particular, the spectral sequence begins from the homology and converges to the this Tor defined over the cochains. And since from part one we see that that's isomorphic to the cohomology of the pullback, then of course we've computed the cohomology of the pullback. Now, I want to point out that this is graded in the following way. Minus PQ, and one can write, one often writes this going to this. That is the, and so this is a second quadrant. Spectral sequence. So it inhabits this area here, and differentials tend to look like that.
What do you mean by the double index for the total?
I'm sorry?
What do you mean by the double index for the total?
Yes, very important question. Right? So this has to do with the fact that I'm making projective resolutions of graded objects, right? And so these are going to be also graded. And so when I do that, let's say I resolve C star x here, the projective thing will have this. This projective thing will be graded like this. This will be graded like that.
You have to put a negative sign
Yeah.
to make it into coaching.
That's correct. That's exactly right. And that's exactly why I need it. And then when you tensor the projectives with C star E on the right, then you have to do that carefully to make that make sense. And then and you make a big double complex out of that. And the double complex can be totalized to compute the tours. But what you're keeping track of is how deep in the projective resolution you have to go for an element in here. And so that this is the filtration degree that records the homological appearance of the thing. And in some sense, this is the adjusted topological degree in a given column. But because of the way the spectral sequence works, together they contribute to this degree. So one way to see this is by way of doing iterated suspensions if you need to do it spatially. So things are moved down in order to become appropriate cochain complexes. And so that's it's an excellent question you ask, because these numbers are meant to be interpreted as geometric, and so one shouldn't lose track of the fact that they are geometric. So what's going on here that forces that to happen? So there's an answer to this question. What's that?
Does it matter if I just change the index in negative, for example, negative 2 and star as a star and negative 2? And then the projective resolution of C star x. So we have double
Yeah.
index, right?
Yeah.
So that is a projective resolution of C star x.
Yes.
So when I index it, if I switch the negative 2 and star and negative 1 and star as a star and negative 2 and star and negative 1, like this way, if I write that way, then
you just change this
change
PQ.
Yeah, that's right.
It's only natural. Because you're not second quadrant, but what is the quadrant?
Yeah, that's right. You're trying to make everything upside down. That's another thing to do, is to make everything upside down. John Moore was very keen on this. I would recommend that maybe John's secret notes be published, except that no one would read them because they're horrible. But he wanted that you should always write everything in, so your chain complexes were, a cochain complex was just a chain complex negatively graded. And so everything was uniformly graded in one way, so that you could talk about cohomology and homology at the same time. And all that did was confuse me. So, I don't know. It's probably a good thing, but be careful. Yeah. I thought it would be fun to show you some calculations of things with this. And so let me remind you, consider the divided power ring on an even degree generator, gamma y2n. And I just mentioned this because I don't know if everybody is familiar with the ring of divided powers. And since the ring of divided powers is so cool, everybody should know about it. So, so let me tell you what it is. Gamma y2n is generated as a vector space by 1 gamma 1 y gamma 2y 3y, etc., with the degree of gamma ry just 2nr, and 1 gamma 1 y to be y. And so now I want to tell you the multiplication on this. And the multiplication goes like this. If I take gamma p and gamma q and multiply them together, I get here a binomial coefficient p plus q times gamma p plus qy. Now, this seems very odd kind of thing to introduce, except let me make an excuse for it, okay? So my excuse will be a kind of spectral sequence, and it goes like this. Let's put down here x in degree 2n plus 1. And let's pretend that this is the cohomology of the 2n plus 1 sphere. And so I'm interested in working out the path loop vibration. And so going along this line here, I'm going to have the cohomology of the 2n plus 1 sphere. And of course, in the path loop vibration, the only thing that's left at the end is the ground field. So there has to be a generator up here in dimension 2n, which goes down to meet that. And as soon as I've introduced that, then I've introduced here a class x times y. And so I want to get rid of this class. So I'm interested sort of in the class that's up here, y squared. But notice if I take the differential on this, dy squared is 2 xy. And so since we're a little bit worried about what the characteristic of the ring of the field K is, I'm worried about who this 2, what this damage this 2 is going to do to my morphism. And so instead, if I put 1/2 here, then of course this would go just fine like that. But so what is 1/2? Well, if I take gamma 1y and gamma 1y and multiply them together, I get here 1 plus 1, choose 1, gamma 2y. So here I have y times y, and here I have 2 gamma 2y So in fact, you can think of this as gamma 2y. And here I'll write x gamma 2y, and the next thing up here that has to go down to meet this should be 1/6 of y cubed if you work it out. But in fact, if you simply put gamma 3y here, the differential goes directly to here. So this pattern continues, and all of these binomial coefficients fit together to make the ring structure on the cohomology of the loops on 2n plus 1 work out exactly to preserve that pattern. So this is, in fact, a very nice ring, and that ring gives rise to these things. So let me point out that the thing that you should notice about this is that if I take gamma y 2n tensor with this, where I send this differential sends that to that, and then I have this ongoing pattern here, where the ongoing pattern is that d of gamma ry is x gamma r minus 1y. Then the homology of this is in fact just the ground ring, because we've arranged it for that to be the only thing left. So so this is a way to build a cyclic gadget. So this leads to the following idea. So suppose H star B, okay, is nice, i.e. It's isomorphic to an exterior algebra on n generators tensor with a polynomial algebra on m generators. So let's just suppose that we have, in this case, the free commutative case. If you're thinking about your Lie groups over the rationals, then of course there's no polynomial part, but there's exterior part, and it applies in this case to this case. So I'm going to build the following object. Let's call this algebra A, and I'm going to build a thing which I'll call K of A, and this is going to be equal to lambda. I'll explain this notation in a second. So gamma tensor with okay. So this is the desuspension. That is, it's take the x here is in even degree. Take it in. This is a generator in one less degree. So suspend it down one less degree. And so K of A here has differential on it. So let me write this part as B, and this part as A. So think of this as B tensor with A, D on 1 tensor A is 0, D on S inverse xi tensor 1 will be equal to 1 tensor xi, and then d on gamma r S inverse E j tensor 1 will be equal to gamma r minus 1 S inverse Ej tensor Ej. All these things lead to the following conclusion, which you can do by induction. H of this construction is just k in degree 0. So this is an exact kind of object. And if I take this object and then I can filter it by letting k minus n star be equal to, let's see, what do I want that to be equal to? Well, this will just be b minus n star tensored with a. Then this gives a resolution of k I'm sorry, a resolution of a with actually it's a resolution, it is a resolution of k. And in particular, all of these take the form something gummy times a, and hence these are all right projective. And so this is a projective resolution, and the homology calculation allows us to show that this is in fact a resolution that's correct of k over a. So having said all that, then I now can compute Tor over a of anything I want. Let's see, I think, so this will be k L, and this will be simply the homology of this complex tensored over A with L d tensor 1. And if I rewrite this as B tensor A tensored over A with L d tensor 1, then this becomes H of B tensored over K with L d bar, and d bar can be deduced from this. For example, the d bar of gamma r S inverse Ej tensor something in L is simply gamma r minus 1 S inverse Ej tensor Ej acting on L. So the right resolution here and then the left resolution there. And so you get a very nice, tight, small object here. So let's take a look at this in a particular case. Say, for example, for a Lie group. So G a Lie group with H star GK exterior.
You're grading your star. It's just the grade of degree of B.
Yeah, because these are all. Oh, I should point out these all have bi degrees. Yeah, I guess I didn't mention that. So the bi degree of gamma R S inverse EI is minus R R times the degree of EI. And the bi degree of an element here of S inverse X J is minus 1 degree of XJ. And the bi degree of everything on the right, all of the A's, is they have their first part of the bi degree is 0, and the second part is whatever the degree is. Okay, so having let's mentioned earlier in the lectures about the fact that it's often the case that a Lie group has an exterior algebra as its cohomology. Let's take a look and see what we get by doing this calculation. This, by the way, of course, the K stands for Koszul, and this is called the Koszul complex for A. So if I do that in this particular case, the Koszul complex looks like gamma S inverse E1 up to S inverse EM, tensor with lambda E1 through EM. And then if I'm interested in the situation where I have the path loop vibration, then since the path space is just is contractible, I have a point and a point. So I'm going to take my resolution tensored over A with K, and then take the homology of this with regard to tensor 1. And of course, this is H of the divided power algebra, and the new differential turns out to be 0. Okay. Let's see, why is that obvious? Partly because when I apply it to something like this, I'll get this tensored with something which has vanished in the quotient that I made here, and so that completely describes the differential. And well, this will be isomorphic, of course, to this. And so the last step of the calculation is this is Tor over H star G K, and this converges by the Eilenberg-Morris spectral sequence to H star omega G K. And so now the question is, can I now reconstruct this from this information? And here's the beautiful fact about this, and that is that everything here in total degree is in an even degree. Okay, if I take and I add these two things together, notice that I will get R times the degree of EI minus 1. This is odd degree. Minus 1 makes it even. And so the total degree of everything here is even. And if the total degree of everything is even, then when you reassemble it, there are no extension problems to solve. Everything is just explicitly right there. And not only is that, but one can argue that the Eilenberg-Moore spectral sequence is a spectral sequence of algebras. And so I've reconstructed the algebra structure by using the divided powers. So I've run over time. This is not much of a geometric application, but maybe I'll mention a little bit of that in the beginning of the next lecture.
This gives you the algebra